Hi there, welcome back to A Slice of Physics. We're now going to talk about conservation of charge and the conservation of current. The kind of questions we'll address in this video include: how does current before a resistor compare with current after the resistor? We already know from our previous discussion of Ohm's law that adding resistance to a circuit will reduce the current in the circuit, but we're now going to look more specifically at the current before and after the resistor in the circuit. And that leads us to another related question, which is: how does current split or merge at junctions in a circuit? Let's begin this discussion by looking at the water analogy again in a pipe. So let's say there's a pipe here that's slanted like this, and it's transporting water from a reservoir at the height here to a lower reservoir over here. So this pipe is going to be full of water, and the direction of flow of water is going to be like that. The reason this water flows in that direction is because I have a high potential here, in this case high gravitational potential, and a low potential here, again lower gravitational potential, which creates a potential difference between these 2 points. We can write that as delta V, and that causes the water to flow. Now let's take another example. Same situation, same pipe, going through the same height difference, except in this case we're going to put a big boulder right in the middle of this pipe. So now we still have the same potential difference between the high and the low point, and there's going to be water going through the pipe as a result. But as you can imagine, there would be a lower flow of water in this pipe. And we want to discuss the flow of the water before it gets to the rock and how that compares to the flow of the water after the rock. So this flow of water is current. So let's call this I1 as the current of water before the rock, and the one after as I2. And our goal is to figure out how these two compare. Well, your initial expectation might be that I2 is less than I1. So in other words, the water was flowing through this pipe at a certain rate. Once it encountered the rock, it slows down as a result of the small volume of passage around the rock, and because of that I2 will be smaller than I1. Well, it turns out that that is not correct. This is wrong. So let's look at this a little bit deeper. The key aspect here is that water is a liquid, and for all practical purposes, liquids are incompressible. And by that we mean that it's got a fixed density. And that is a key difference between gases and liquids. If you take a glass container, let's say, and put some gas in it, and then you put a plunger and squeeze it down, you can reduce the volume of that gas and thereby increase its density. But if I take a similar glass and fill it up with some liquid, well, the liquid will first of all assume a certain volume that's dependent on what its density is. And then if you put a plunger and push it down, you can't compress the liquid much at all. It's either going to want to bulge out of here or create a hole and leak out, but the density of the liquid is fixed. So what does that have to do with all of this? Well, there's a certain amount of water that's flowing through this pipe. So if, based on this naive assumption that I2 is less than I1, I've got more water coming to this rock and less water leaving it, which means it's bunching up and getting collected over here. And if the pipe's dimensions are not changing, that can only happen if the density of the water here is higher than the density of water after the rock. And we just discussed being a liquid, that's not possible. The only other way to do it is if it creates a leak and leaks out, but in that case the situation changes. So we are forced to conclude that given that liquids are, for all practical purposes, incompressible, you have to have the same current before the rock as you do after the rock. Now it is true that given the same potential difference, putting the rock here creates a resistance in this second situation. So let's call that R over here for resistance, and adding a resistance will decrease the rate of flow compared to when you had no resistance. So if the current in this situation was I0, I0 is greater than I1. But the important thing is it decreases the current everywhere in that pipe, before the rock, after the rock, all through it. Unless there is a junction in the pipe, the current in it has to be the same at all points. By analogy, that same argument is true in circuits. So if I have a circuit here with a battery connected across its two ends by a wire, so this would be our low resistance case. You remember from previous discussions that wires have negligible resistance compared to bulbs and other resistors. So the current in this situation will be quite high. And you know current goes from the positive end of the battery to the negative end. So I'm going to have a current I over here that's created by the potential difference between these 2 points, delta V, which is the EMF of the battery. And if I take that same battery and now simply add a resistance to the circuit over here, once again we want to compare the current in this circuit specifically before it gets to the resistance, so I1 over here, and after the resistance I2 over here. So same situation as we discussed before, it's just that this is the electrical analogy of this gravitational water flow. Now you know that these sections of wires have lots and lots and lots of electrons, so it's a very high density of electrons. Any small piece of wire would have more than 1 trillion electrons. And so electrons in a wire act similar to liquids in the sense that they're already packed very tightly and they can't be compressed. And so the same argument holds good in this case also, and that tells us that I1 has to be equal to I2. And by the way, I can show I1 over there or over here as well. Since these are ideal wires, there is no potential drop across the ideal wire. So I1 is literally the current coming into the resistance. I2 is the current that's leaving the resistance. And those two have to be equal because of conservation of charge or conservation of current. We can't destroy charges here. We can't create new charges. And that tells us that the flow rate has to be the same before and after the resistance. And as before, if we call this I0 or I0, this current I1 and I2 are both less than I0 when the resistance was a lot lower. So hopefully this helps you address the confusion of, when you add resistance, current goes down. That is true. But it's not true that the current goes down only downstream of the resistance. It has to go down in the entire circuit as long as there is no junction that gives the current somewhere else to go. All right, now let's talk about junctions. So let's say I have a circuit that looks like this. I've got a split, and I got one bulb here of some resistance. I got a different bulb here, and let's say the resistance of this top bulb is a little bit lower than the resistance of the bottom bulb. And this is how the wires are connected across a battery. We'll talk more about the arrangement of these bulbs and what that does to the resistances later. But for now, all we're interested in is seeing what happens to current in junction. So let's say the current coming out of this battery is I1. When it comes to this junction, this current is going up over here and to the right over here. So I got current I1 coming into the junction. And then here it splits in two parts. Some of it will go to the top section, some of it will go to the bottom section. And as we said before, this resistance of this bulb is a smaller number, so I'm going to call it R low. I'm going to call this R high to show that it's a higher resistance bulb. And so by common sense, we would expect more current to go in the segment of the circuit which has a lower resistance. Also by Ohm's law, that's consistent. So if I have I2 over here and I3 over here, we know that I2 is bigger than I3, but that's not the point of our discussion. We want to see what happens at this junction. How are this I1, I2, and I3 related? Well, once again, based on the conservation of charge and the conservation of current that we discussed here, we can't create or destroy charges, we can't create or destroy current. So the total amount of current coming into the junction has to equal the total amount of current that's going out of the junction. So that's called Kirchoff's junction law. So by Kirchoff's junction law, the sum of the currents coming into a junction has to equal the sum of the currents that's leaving the junction. So that's the general form. And in our case, that translates to I1 equals I2 plus I3. Now, based on what we just discussed here, if we just look at this top segment, how is this I2 connected to the current that's in the wire after the bulb? So what would this current be? Well, once again, as we discussed, all these electrons have nowhere else to go but to keep going through the same wire, and since they can't pile up anywhere, this current after the resistor also has to be I2. And similarly, the current in the bottom circuit after the bulb has to be I3. So now let's analyze the second junction over here. So the current that's coming into the junction, sigma IN in the second case, would be I2 plus I3, because both of those are coming into the junction. And so if we ask the question of what this current over here would be that's leaving the second junction, well, that's got to be I2 plus I3, which, as we saw before, was simply I1. So the current that's leaving over here is I1. So to make up some numbers here, just to give you a numeric feel for this, let's say the battery had 10 amps of current coming out of it. And because this is a lower resistance at the top, let's say more current went to it, and let's just make up a number and say 6 amps went up over there. If we know those two numbers, we can immediately determine the current in this bottom circuit. Since 10 is coming in and 6 is going there, this has to be a 4 amp current going over here. And after the resistance, the current would be the same, so I'd still have 4 amps over here, I'd still have 6 amps over here, and exiting the second junction over here, I'd have the 6 plus 4, 10 amps leaving it, and coming back over here would still be 10 amps. Okay, this is important law to remember because we will be applying this quite a bit as we work with circuits. In this slice of physics, we discussed conservation of charge and conservation of current. We saw how this plays in circuits, and yes, as a result of adding resistance to a circuit, the current in the circuit does reduce. That is true. But that leads us to believe sometimes that the current only reduces after you cross over the resistance, and that part is not true. The current before and after the resistance in a wire has to be the same because of conservation of charge and conservation of current. So the current before and after the resistance both get equally reduced when you add the resistance. And that led us to Kirchoff's junction law, which told us that at any junction in a circuit, the total current entering the junction has to equal the total current leaving the junction. Thanks for watching. I will see you later.